for joining this webinar. Uh, Thanks for joining this webinar. The idea is to get present some concepts on wellbore performance, both in the inflow, outflow, and of course the two. When you get those two, basically it's wellbore performance analysis of what is commonly, using a trademark like Nodal Analysis. And so basically, matching the inflow capability of the reservoir to outflow capability of the well is, of course, is a requirement to predict the coupled reservoir and wellbore. That's a key concept, because normally you hear everybody saying reservoir performance. It's not reservoir performance only. It's reservoir and well performance. It's the couple. The reservoir without the well, it doesn't mean anything. Or the well without the reservoir, same. So it is, but wrongly people are, especially reservoir engineers, they said reservoir performance. Again, it's not, it's the couple, reservoir and well performance. So this matching will give the operating condition of the well at the given reservoir and well condition. The moment we are going to do the analysis is a particular moment. It's like a instantaneous picture, because we don't stop the condition of the reservoir, the flowing, the pressure and temperature. Everything, if it's of course, if we have a well on production, everything is changing. Pressure is changing, decreasing, the flow conditions in the wellbore, and through the perforations, if we have perforations. So there are many changes. So it means whenever we are doing an analysis, remember there is a particular moment in the life of the well, but we need to continue coming back and updating this model, because this is a model, and so the closest we have this model to represent the conditions of the reservoir and the wellbore, then the closest we are to really predict the performance of that such a coupled well and reservoir. Because the performance is part of the reservoir and part of the connection reservoir wellbore, which is completion. This is the definition of completion. Is not, that's another common, let's say, misunderstanding from industry. They said, you hear upper completion, lower completion. We are, in the technical definition of completion is the connection, the wellbore to a reservoir. How you connect the reservoir to the wellbore in order to get the optimum performance of that well. So in that way, part is due to the tubing and surface lines up to the separator. Any problem on those components, which of course will lead to a non-optimal well performance. And so we need to think of a remedial action once of course, we identify the cause of the miss or the poor performance. Inflow problems. So how we, again, see inflow problem is defining as the performance from the reservoir to the wellbore. Remedial action and stimulations, either acid or fracturing, depleting, enhanced oil recovery plans. Outflow performance, so it is the tubing. We are talking about the tubing, remedial action is talent if we don't have, if initially the well was flowing naturally, but of course now it reached to a point where it is not able to produce the fluid up to the surface. So we need to install an artificial lift, or we need to increase the shock size or decrease the wellhead pressure, maybe changing the tubing size, flow line, etc. And inflow and outflow problems, so we need to think of a workover action. Inflow performance, now we will be talking about the inflow performance relationship. Is really a mathematical representation of the reservoir ability to deliver fluids to the wellbore on the expenses of the bottom hole pressure. For an ideal wellbore, no damage, no stimulation, the IPM might be made by the equation in this form: Q over Q max, 1 minus 1 minus X times the pressure, the well bottom hole pressure, flowing bottom hole pressure, static pressure, and then the ratio flowing bottom hole pressure starting. We will see why this form. X is a numerical parameter which determines the specific IPM model we are using. For instance, when X is 0, we have a linear IPM model. When X is 0.8, this we are talking about the Vogel's IPM model, or when X is 1, we are talking about Fekkovich model. For a real well, with either a damage or stimulation, a flow efficient might be concept instead of the definition as we saw for a ideal well, not damage, not stimulation. In this case, we have, of course, we have damage. So the flow efficiency is a function of the the static and the flowing pressure, but also in this case, the delta P skin is coming into the equation. So then this is the definition: flow efficiency. Delta P is pressure to the skin. Later on, we will see what is what we call pressure drop to skin. So this equation leads to another one, including the skin factor concept as right here. This one, we have the F. We just calculate the flow efficiency, and the Y ratio, which is one minus flowing pressure over static pressure. If the well is tested at two different rates, this equation could be used to calculate flow efficiency. If only one test, then S should be obtained from another test. A linear IPR, in this case, we will see how to work with this generic equation, the one we define, equation A, we call. In this case, in the linear IPR, in this case, X is 0, and then the equation reduces to this as we have right here. Remember, if it's linear, it means we are above the bubble point pressure. So that's the requirement to get the linear performance. The flowing pressure should be always above the bubble, pressure. And then we have the definition here. The new flowing bottom hole pressure is the traditional bottom hole pressure plus the delta P skin. And then Q is equals to the J, which is the productivity index, times the differential pressure between the reservoir and the wellbore. So this is the classical definition of in for linear performance. So J is constant. So it is we can with this we can define either Q if we get knowledge of the flow performance, bottom hole pressure, and the rate. We define, of course, and also static pressure. We define the productivity in this. The skin effect have been absorbed by the I mean, the J factor. This equation allows the prediction the inflow capability of the well. If the static pressure is higher than the ball pressure, of course, should be, as I mentioned, should be J is constant. A linear for a single fluid flow and a pseudo steady state condition, then the PI is defined more like in field units. Right here, we have now KH, viscosity, the volumetric factor, the radius, external radius, wellbore radius, plus the skin. So for a restrictive well performance, the parameters that can be modified in the easiest ways are viscosity and skin. So, um, so viscosity can be increased by thermal actions. Skin can be decreased by doing some remedial action, provided we define properly what is the cause of the skin. For instance, normally we have high skin. Normally the companies they like to run an acid job, but this is, I mean, again, to run an acid job, I mean, the skin doesn't mean that is damage. You know, damage is part of this X that we have right here. Another components of this skin is relative permeability changes, um, and wellbore not really, I mean, in a wellbore, I mean, radial model or near a fracture. So many things changing. So it means even though we have an high skin, it doesn't mean that always is damaged. So that is why it is only if you are thinking of a acid job, that is only uh, possible if the material cement in the pore is acid soluble or any, I mean, so, or in a carbonate, but that's a different story. In a carbonate, no doubt, the acid will improve the performance, but in a sandstone, we have to be careful. That's the message. So, when with viscous oil, of course, the viscosity reduced by thermal mean, steam injection, and the skin should be decreased accordingly. If K is too tight, you know, reviewing the parameters of the question right here, a negative skin can be attained by hydraulic fracture. That that's really a stimulation. There are only two actions that we call really a stimulation. One is this hydraulic fracture, because in that way the final skin is negative. So it means -1, -2, it depends how good we perform that job. Then we have negative skin. And the other one is a acid a carbonate. That's the second one. So those two are the really acid stimulation, fracture, hydraulic fracture, and acid carbonate. So beyond that, you know, doing this, you have a problem with the wells. Normally, people say, we will do an acid stimulation. That is not acid stimulation. When the skin is positive, you are trying is to damage remediation. Damage remediation is not stimulation. So I hope this is clear concept. Um, damage during drilling, completion, or production very carefully, as I explained. Um, for multiple flow, K is multiphase. K is replaced by K times relative permeability relative to the oil. Pressure reduction with production, the reservoir is depleted, of course, and so the PI declines. Predicting the future PI is related to the present PI, but this equation. So here we have this equation, present productivity index and future productivity index. As we say, we see it is a function of course, the the parameters that depend on the pressure, like permeability, relative relative permeability to the oil, viscosity, and uh, volumetric factor for the oil. So, and then because they are dependent on the pressure, and so Vogel is the IPR model. Now we see how it's calculated. In this case, as I mentioned at the beginning, x is equal to point A. Then the question becomes, this is the classical Vogel equation, 1 minus zero point 0.2, and the ratio of flowing pressure, static pressure minus zero point 0.8, and the same ratio to the square. In this case, this model describe a well, ideal well again, and damaged and stimulated below the bubble point, the pressure. Then, yeah, it's not constant anymore because it's basically is declining, and is this is only for from the point of the bubble point to the below the bubble point performance. So it is right here. Um, when Mr. Vogel worked on this, he basically had on this the left plot is the ratio from 0 to 1 on both axes. But when it's Q times or versus the bottom hole pressure is the one to the right. So it means the IPA model is Vogel's, the green the curve, and the linear, yeah, we put the linear model that we explained at the beginning. So Vogel Futures IPA is wasn't somebody standing work on Vogel's equation to get the future IPR as given by the question, where the future is the given by the question, this equation, and the pressure, the future pressure is the future average pressure of the reservoir. So it means in this case we also can calculate the future performance of the well by using this equation. So Kovins comparing the two to with question with concept that simple concept, but just to why does a well flow? Pressure different, of course, but the question is where. On the surface, of course, the wellhead pressure should be higher than the separator. The we have to bear in mind that this couple is, I mean, this pair of pressures, they are linked together. I mean, it means if we lower the pressure of the separator, we will be lowering somehow the wellhead pressure, and that is good for the because in that case we are all also lowering the well downhole flowing pressure. So in the well, of course, then the flow pressure downhole should be higher than the wellhead pressure. And in the reservoir, of course, in the reservoir, of course, oh, sorry, in the reservoir pressure, of course, it should be higher than the flow pressure. In this case, we have flow continues to from the reservoir to the separator. So, how then the question is, how good is a well? Uh, what do you get for the effort you put to drill a well and produce the well, complete the well and produce the well? How how productive is your well? Um, Productivity index, of course, then it comes to play a role, and just to tell us what is how good is the well. Is this question we have right here, Q equals pi times the differential pressure, is a reservoir equation, is an inflow performance. Uh, how, why does a well decline in production? That's the question. So using the same equation, this we have right here, of course, the rate is a function of the PI and the difference between the static or the reservoir pressure minus the flowing pressure. PI it could be decreased. Why? Because maybe some production, a scale at the perforation, gas blockage. PR, why? Of course, it will be declined because PR decline. It means lack of pressure support. So we don't have an active water support or gas support from the gas cap or whatever. So basically, is a reservoir on gas solution, basically, and flowing pressure will increase due to increasing water cut or increasing wellhead pressure. That's why, again, I mentioned before, it's key to keep the wellhead pressure to the minimum possible in order to um, reduce the flowing borehole pressure and be producing the maximum. How to increase the well production? So it means we are talking about optimization. So it means um, how to increase here this. So PI can be increased by stimulation, reperforation, clean out, and basically those are skin components. The reservoir pressure could be by injecting water or gas, if possible, of course, by decreasing the flowing pressure, the wellhead pressure should be decreased, or we need to open the choke in order to decrease the bottom hole pressure. And also the other option is we don't have the well was flowing naturally. Now we have it's time to consider installing artificial. Um, we will be touching on well flow analysis concept, reservoir and well inflow performance. Again, as I mentioned at the beginning, is not well performance as everybody's, even talking, oh, well performance, well performance. It's not only well performance, it's reservoir performance and well performance. Part of the performance, again, is due to the reservoir, and part of the performance is due to the well. So that should be clear. Well, outflow performance, and then the other component is total well reservoir system analysis. So Darcy's law definition, um, Mr. Darcy, I mean, we are the oil industry just use Mr. Darcy equation and then adapt it to the reservoir, but ideal reservoir, wellbore, radius and single flow, homogeneous, no damage, no stimulation. So many things, that are really, I mean, they take original. This is in the beginning, reservoir engineers, they took the core data, PVT fluids, assuming homogeneous reservoir, single fluid, circular drainage, low velocity, non-damage, non-stimulation. And then they calculated the performance of the using Darcy's equation, and they define right here the green curve. But that was again, whenever we put the well on production, always we have the depending on if it's we didn't get really that performance. So there was something, a discrepancy between that inflow calculated using Darcy's and the real performance of the well, which is the red curve right here. So what causes the additional pressure loss? See, we have right here is between, depending on the rate, we have for this, for instance, for 1500, 15,000, we have an additional pressure right here. And for that is right here, the discrepancy, depending on the rate, there is, of course, the discrepancy, the higher the rate, the higher the discrepancy. So anyway, so what is causing the additional pressure loss? So then the problem was that the reservoir was characterized, but the well was not characterized. That's why they have this discrepancy. A standard methods predict flow through a reservoir, but not predict the flow to, into, and through the well. So it means the standard method do not take in consideration the completion effect. So completion effect, completion, again, I define connection to the reservoir, breaking the effect of the completion, connection well reservoir is a dominant feature. It dictates how fast you can flow the well. The simulator predict the pressure loss, and the pure Darcy flow is 100% flow efficiency. But skin is any distortion on the ideal flow performance, perforation, drilling, invasion, gravel packing, causing extra pressure drop above or below the ideal flow performance. As there are some alternative well performance measure, completion control parameter we call, length of the perforation, permeability in the annulus, wellbore screen, if you have a screen or a liner, that permeability in that, or perforation on the tunnel permeability, on the, of course, permeability in the perforation tunnel, Those are parameters that dominate the pressure losses, and each completion has their own parameters. So it means if we think a gravel packing, the skin is really high. If we, as mentioned also before, if we are thinking of fracture, really low permeability formation at the and the skin associated to that fracture, it is negative. So in this case, is a good for the well. So and then so in between we have open hole, we have perforation, perforated case hole, perforated. We have uh, so many completions. So each type of completion again has their own skin value. Those parameters will tell those parameters defined right here, length of perforation. So define if we did a good job or not. So completion pressure loss is an important component of the total pressure loss. Well flow analysis techniques should understand the flow through the completion, but that again, that's the nobody is considering that. The software parameters normally they don't consider that, so we have to be aware with this. So flow through the completion to include is resultant pressure loss to effectively model the well and reservoir couple performance. So completion, for instance, in this case is a representation of the perforation. So perforation time and permeability provides a good measure of rating the case hole gravel packing and case hole flat pack. So there are, those lines, black lines right here are lines converging into the perforation. That's why another skin in this case is the converging effect. It's another skin, so it means if we compare the flow of an open hole and then compare with the perforated completion, of course, in this case, because of so many additional skin values, we are basically in this case, we are having a higher delta P skin because of those concepts. The determination of the skin factor, the most important effect is perforation length in the well flow efficiency. Shot density plays a less important role for a hard rock. Is how deep you, for instance, right here, the brown area is a damage or more invasion. So by getting a long perforation tunnel of deep penetration, we are overpassing that area. So, I mean, in this case, we are, getting the flow from the non-disturbed flow or reservoir. So, right here, so we get some variables, the perforation length, how versus the skin, depending on different configuration. For instance, shot per foot, density of perforation, 4, 8, 12, 16, 20, or the inclination also of the wellbore. And or the last one, the blue one, is when the is the best because but the is highly inclinated because if you are inclinated well, also that it will give you a negative skin. So same for on the that's on the plot on the left. On the right we have the comparison for reservoir normalized permeability in the perforation tunnel, um, uh, permeability at the tunnel versus the permeability of the ratio. Of course, the higher this ratio, then you are moving to the right, and then the flow rate is increasing. So those are some simple calculations, simple that we can do before running any tool in the wellboard. So basically, we don't need to go and run tools and do experimental things. If we have, we can model this and we play with this type of plots. So basically predicting the effect of the compression, for instance, the perforation of the TCP versus to tubing perforation, is a big difference. The often TCP is, of course, when compared to the another perforation run on one line is right here. So, all right. I think for now we can stop here and continue tomorrow. We start tomorrow um, with the